Welcome to the next video lab discussion. This is the next step in a series of lab discussions that support an introduction to RS-5000, part of the complete PAC Learn series. This particular lab in the book, in the manual, was changing the processor type, adding I/O modules to your project, building your data neighborhood. And in this project, we're going to take an existing project and change the processor type to see the effect on the I/O configuration. And then we're going to delete some I/O modules and add in other I/O modules. Depending upon what order that you're doing these lab projects in, the order in the manual, or you've looked at the table of contents and picked out the ones that you were interested in, these labs were not done in this sequence. In other words, I did not create them in this sequence. As I thought and considered what you might be interested in, what you might need to know in the field, I would create these labs as the ideas came to me. Then after I had, a couple hundred pages created, I started to arrange the labs in some sort of sequence. Whereas with the Complete PLC Learn series, which was based on RS-500, those were done in an absolute sequence, and they're in the manual in that same sequence, and you almost have to do them in order for them to make sense, or I should say for the program file to be in the state it needs to be in when you start the next lab. In this manual, this is not the case. So we have made a few adjustments to try to make it blend a little bit better. However, since we're doing three different types of processors, we're doing control logics, and then we're doing two compact logics, L35E and L45. We need either an L45 or control logics to do motion. The L35E, which is the least expensive of the three, does not support motion. At this point, we're going to switch the project over to an L45 from an L35E. I'm going to take you through that process and point out some of the things that you might run into. And this is a possible scenario that you could go through in the field where you have a machine with an L35E on it and everything's working great, and then some more equipment needs to be added into the process. Maybe there were some cylinders that were doing some motion, or stepper motors, or some other form motion control, and it wasn't quite working out. It didn't give you the precision that you needed, so you needed to go to a servo. The L45 and the L35E aren't exactly the same size, but they're close enough where they would fit in the same spot in the panel, and they both do snap onto DIN rail. So it would simply be a matter of removing the L35E and its power supply, because the power supply is a 1769 power supply. It won't work with an L45. And then you would replace those two components with the 1768 power supply, the L45 processor, and then of course you should provide Ethernet. Now Ethernet was built into the L35E. It is not built into the L45. So you would need to add an Ethernet bridge card. Now the Ethernet bridge card for 1768 is much, much more powerful than the Ethernet interface on the L35E. And then of course for motion, you're going to have to add a Circos card. That does take up a little bit more space in your panel. It's not going to be an exact fit, especially lengthwise. But typically, if the panel was designed right in the first place, this type of feature was considered in the panel layout. That is, typically panels should be laid out with 20% minimum 20% spare space, meaning that any area of the panel, any component designation, any category should be able to expand another 20%. In this case, the L45, its power supply, the Sercos card, and the Ethernet card would just fit into that 20% category. So this is a very doable scenario out in the field. So we're going to change the processor type, and to do that, we're going to save our program here. If you just finished up with the conveyors with the multiple programs, remember we had line 1 conveyor, line 2 conveyor. And by the way, we did mention add-on instructions as part of this section, and all we really covered on add-on instructions was that they were part of the granularity available in RS Logix 5000. Within a routine, like this is a routine, you could create an add-on instruction that basically contained this logic. And then you would have to bring the outside world in. In other words, you'd have to bring in system enable, you'd have to bring in this tag, this tag, this tag, and then coming out you would have this tag, and then this logic would be inside that add-on instruction. You would not create an add-on instruction like that. That would be a waste of time to take logic that simple and make it more complicated by making it into an add-on instruction. So we're not actually going to create any add-on instructions in this manual. Add-on instructions is a fairly complex procedure if you make one that really has some functionality. That's going to be done in volume 2. So moving on here, we'll save this, but we're going to save it as. Instead of going up the floppy disk, we're going to File, Save As, and we'll call this processor change. Now I probably already have one in here called processor change. Nope. Well, good. So we'll go down here and we'll call it processor change. The only reason it's good to do that is so you can revert back to a program before you start making the next set of changes. So it's always good to save your program and rename it. Now, I didn't tell you to do that in the manual, but it's always good practice before you make changes to a program to make a copy of it, meaning save as, give it a new name, and then execute your magic against the copy. That way, if you mess it up, you can always go back to the original. Okay, we saved it, we renamed it. Let's go offline here. Now, the processor button is right there, controller properties. We're going to open that up, change controllers. Now we could change the name of it too. Now we'll just leave that. We'll leave it conveyors. Change controller, go to the list. It's going to be higher up in the list. Oh, there it is right there, L45. And of course, we're going to leave it version 20 because the program that it's in is version 20. We'd have to create a whole new program or go through a conversion process. And of course, you need to read through this. In our case, we're going to click yes no matter what. But there are some important notes there. Changing the controller type will change, delete, and invalidate controller properties and other project data that is not valid for the new controller type. Go figure, right? Naturally. Modules not supported under the new controller type will be deleted. Now in this case, the modules that we used before are supported. Even though we're going to delete those modules and put in different ones, they are supported under the new controller. But if we were going from an L45 backwards to an L35E, there are modules that we're going to add to the L45 that you could not go backwards to the L35E with. Get system variable and set system variable instructions will no longer verify if they reference a deleted module. Also, the only GSV or SSV that we used was the GSV to get the time and date. And the controller object that we GSV'd probably is the same for this controller, or I should say the wall clock time is identical. That object is probably identical from controller to controller. Okay, MSG instructions may target invalid modules or serial ports. That's because message instructions follow hardware paths. When you define a message, a SIP, Common Industrial Protocol SIP message, you define a path. And if your hardware image changes, in other words, your I/O tree, your I/O configuration, the path changes and it may no longer be relevant. Consume tags will be deleted when the producing module is deleted. In this case, we're not doing any producer consumer yet, so and that'll also be in volume 2. You read down through the notes, you click yes. Now, I'm going to click no here and go back to this because there's something I wanted to do. Okay? I want this visible right here. I wanted the I/O configuration visible when I did that. So we'll go right back to where we were at, to the L45. Click OK, and we're right back to this message. Now watch, keep your eye on this area down here. We click yes. So it's going through and it's editing the project to make the changes for the new processor. Notice that this did change. The Ethernet is gone. But because the 1769 IQ16F and OB16P are supported modules by the L45 on its 1769 bus, they're still there. Go to the module defined tags, you see they're still there as well. So we didn't really lose anything except for the Ethernet port. And we're going to add that back in. Now these two I/O modules, the OB16P and the IQ16F, are not the modules that I have physically connected to the L45. So we're going to delete those and add in new I/O modules. And when we do that, you want to pay particular attention to these module defined tags to see if there's any changes there. So you can always open up an old project to see, but you can see you have 2 for the IQ16F. The first one and the last one are for the input card, and the 3 in the middle are for the output card. So really the only big thing that was noticeable is the change of the I/O configuration. You lost the Ethernet port, or the, if you want to call it, daughter card that was in the L35E that supports Ethernet. Also notice that the error display came up, and this is typical whenever you verify a program or do just about anything. It will come up, it will pop this up, and of course you can remove it, you can drag it down as such, or you can just delete it. Now, the bottom of our processor properties box is off the screen, and I can't quite get it up to where you can see. Maybe you can see the edge right there of OK. So I'm going to click on OK, and now we're back with the exact same project, only we have a slightly different I/O configuration. But notice that these tags are all still good because nothing changed on the 1769 bus. See, we still have the OB16P in slot 1 and the IQ16F in slot 2. Okay, now we're ready to delete the 2 existing modules because we want to use a different set of modules, simply because these are the 2 modules that are attached to the L35E that I'm using, and I have different modules attached to the L45. Now I could swap these modules over, but I wanted you to see this procedure in case you need to do this in the field. I've collapsed most of these areas here. If I hadn't done that, then we wouldn't be able to see what was going on outside of the view. Typically, you wouldn't collapse these, but you see I've got this collapsed down to the bare minimum, just I/O configuration expanded. It doesn't matter what order you delete them in. We'll delete this one first. You right click on it and then hit delete. delete the module. Now notice what happened. Look over here at your logic. Now you've got some E's in there. We just deleted the output card. If we go over here and click on this guy, that was in slot 1. Is they're now a local 1 0 or local 1 O data.0. See, there's a local 2, but the local 1 is gone. So this tag right here is now in a strange condition. It was valid and now it's not. So these are things you need to be aware of. Now, we're going to go delete this card. Oh, by the way, data types, notice, these didn't disappear. We just deleted the output card from slot 1, but the module-defined data types that support that module in memory, because you remember that in RAM you have a virtual hardware configuration, and it's based on the I/O configuration down below. So memory is organized in a sense to represent a virtual I/O configuration, and each object in that I/O configuration has a memory location where data is stored. For that output card that we did have in slot 1, local 1, these 3 tags, structures, these are classes of objects, and instances of each of these was in place in the virtual I/O configuration in memory to represent that output card as far as its data goes. Because remember, the data in that part of memory will match what is sent to the output card for configuration, will match the structure that you send data to control outputs, and it will match what comes back from that output card back into memory as far as input information goes. So now let's delete this one. Right click. Now that's off the bottom of the screen. Well, here, let me collapse that. Right click. There it is. Delete. Okay. Now we didn't get any more E's, but now all of these I/O tags are in dire straits. None of them are legitimate. Now some, as a matter of fact, they won't even come back. I didn't do that on purpose, but in my new hardware configuration, when we add I/O modules back in, they're not in the same order that they were in the L35E. So if you were going to mix it up on purpose, you couldn't do a better job than we've done here by accident. So now we've deleted those, and once more, those tags are still there. And you could leave it just like this and change these actual real I/O tags that really aren't legitimate anymore, that they don't exist in RAM. That's just text. Okay? You notice when I mouse over that you're not getting what you normally get. Okay, there's one that's good, right? If we go here, undefined tag. See, they're all undefined now. So you have 2 sets of text here that don't mean anything. That's an undefined tag and that's an undefined tag. So you're aliasing an undefined tag with an undefined tag. Now, of course, you can't leave it like that. You'd never get rid of the E's and download it in this condition. So the next thing we're going to do is we're going to add in some I/O modules. Now, if we were to add an input card back into slot 2 and an output into slot 1, then these tags would all come alive again. They'd all be good. Now, since we hosed the alias, if we restore the alias in the memory, then this tag that says undefined would probably suddenly become defined, because if you right click, see, it says edit conveyor properties. It doesn't say new. It says undefined, right? Normally when it says undefined and you right click, it says new _2 conveyor running, but it doesn't. It says edit. And if we went down here and made it a base tag, well, let's just do that. It's not going to hurt anything. This wasn't in the lab, by the way. So we'll change it to a base. Now that, remove the alias 4, apply. Oh, doesn't like that. The data type cannot be found or the format is invalid. Oh, data type, I'm sorry. I need to make it a Boolean. See, now it's good. Okay, so now this is a defined tag now. But notice it's not aliased to anything now. So basically all I did was remove the alias and made it a Boolean, redefined it, or edited it, not redefined. I edited the definition of that tag, and now it's a good tag. And we could do that with all of them. But we don't want to take the time to do that. So now let's add some modules. So this is the 1769 bus, and this is the 1768 bus. Okay? Notice that the processor is shown on both. Now, if you're not familiar with the 1768 processors, they set in the middle of two buses, meaning to the left is the 1768 bus and to the right is the 1769 bus. So with this processor, you can use both 1768 modules and 1769 modules. Now there are not a lot of 1768 modules available, and the ones that are mostly bridge or communication modules. So let's go over here to the 1769 bus, new module, and then, you know, we've been through all this before, so I'm not going to elaborate, but in the first slot, I have an IQ16. So I'm going to type in IQ, and there it is right there. Now we had an IQ16F before in slot 2, now this is in slot 1. Okay, but we're still going to call it DC underscore in, only 01 this time instead of 02. It's in slot 1. And we'll disable the keying, and we'll bump it up to 3.1. Actually, if you disable the keying, this becomes irrelevant. And you know what? I don't even know what that module is. Just for grins, let's see if we can do this without messing up this recording. We're going to go to RS links, and we'll pull it down in view here. We're going to go to RS Who. You can have as many RS Who's as you want. You can have RS Who 1, RS Who 2, RS Who 3. They're just little apps that you can open up in RS links to browse. And you know what? I don't have it plugged in to the processor. So we'll see if we can get away with something on the fly here. Okay, I paused the recording just for a second, and I went over and pulled the cable, the RS-232 cable, out of the L35E and plugged it into the L45. Now the L45 does have a COM port on the front of it. It has an RS-232 port. It just doesn't have Ethernet. Ethernet has to be gained with an Ethernet bridge card on the 68 backplane. So we'll go to our DF1 driver here. Ooh, there it is, L45. Expand it, and we'll pull this down a little bit. And now see, we have the same structure you see basically in the IO config in your project over here, down here. So let's expand the 1769 backplane. Okay, these are the modules that we're going to add. Okay, right now we're adding this one. Okay, Rev 3.1, that's what I wanted to see. Now you could do this on the fly, 3.1, 3.1, and now these are the analog cards. And I don't see 2.1. Okay, if you didn't see what I did, I right-clicked, Device Properties, 2.1. So the analog cards are both 2.1 and these are both 3.1. Okay, now that's an RS Who, which was in RS Links. Okay, so I'll collapse that back down. Now notice I did this while I was adding the IO modules. You don't have to stop everything and cancel what you're doing. You can just go open up RS Links, drill down and look at the properties, but you got to do that online. I mean, you can't, this software isn't a mind reader. You got to have the cable plugged in, and you got to have a driver that's communicating with the processor in order to go through the processor onto the backplane, look at the modules, and determine their rev level. So we'll say OK for that one. Now, these changes will cause module data types and properties to change. Remember, the only reason I'm even reading this and pointing it out is because we are actually changing some things. Okay. And this is OK. Now, I'll move that over a little bit. I don't see anything changed here yet. Okay, we added an IQ 16, and this may be the only tag that's needed for the IQ, whereas this one and the bottom one are needed for the IQF. I don't actually know myself, and I'm not even going to check into it, but I'm just pointing out that nothing changed here when we just added that module. Now we're going to go up here and we're going to add an OB 16. Remember, we had an OB16P. Now we've got an OB16, and create, and again we're going to call it DC out 02 this time. Going to go to change, we'll make it 3.1, and we'll disable the keying. Now if we make it 3.1 and that's what the module is, we don't have to disable the keying. I typically disable the keying when I'm doing labs because this is not a real application. Now, out in the field, if you were doing this, you wouldn't want to disable keying. And the difference between compatible and exact match is the difference between the major rev and the minor rev. The major is 3 and the minor is 1. If you pick compatible, then the card has to be a rev 3. If you pick exact match, then it has to be a 3.1. The minor comes into play. If the newer rev level supports features that you're going to use in your program, then you need an exact match. Now, it'll run on disabled keying, but once you've commissioned this in the field a year from now, and some long-haired leaping gnome needs to replace the I/O module, or at least just thinks that they do, and they just grab one out of the parts room and slap her in there, if it doesn't have 3.1, then this whole thing's not going to run. It's going to fault. In other words, it won't accept it. It'll allow you to put it in there, but it won't interface with it properly, and your program won't run. So I just disable the keying just to get rid of the problem or any possibilities for doing the lab. Okay, made the change. I don't see any changes over there yet. Okay, and close. So I don't see any changes here that took place when we added now IQ16, OB16. The other was IQ16F and OB16P. So there would be some slight differences, but you see nothing transpired under module define. These didn't disappear when you deleted the module, and no new ones appeared when you added these two in. Now if we added in another output card, just for grins, this isn't part of the lab, but while we're talking about this is typically what I do in class. So we'll add in I unchecked digital. That's not what I meant to do. I meant to get rid of all of them and then check digital. Okay, we'll try this one. We'll add that one in, and that would be AC underscore, that was an output card, right? No, input card. N03. And we'll put it in slot 3. We won't change it because we're going to turn right around and delete this card. And I don't see any new tags in here. So it's still discrete. It's still a digital card, even though it's AC instead of DC. So we haven't invoked any new module defined tags. So I'm going to go back and delete this because we're running off into a direction that I didn't intend. But this is typically what I do in class when I'm teaching class in person, is we do a lab and then I go through and discuss it like we're doing right now, And I might go anywhere, whatever pops into my head, whatever questions you ask. Well, Mr. Gates, what if I were to use this module instead of this one? Well, let's go look. And so we have a processor, we have RSLogix 5000, so we just go do it. Okay, I hope that didn't confuse you. So basically all we did is we deleted the 2 discrete I/O cards that were there and put 2 back into the same spot, but we swapped. This was output input, and now it's output input the other way around. So these tags still aren't any good because slot 1 is not output and slot 2 is not input. We can easily correct that by editing this tag. Now this one, since we removed the alias, let's go add the alias back in. Now that was bit 0, I think. And okay, we'll type in local here. Local input data 0. Okay, and we would go over here, edit, and this is going to be, a matter of fact, we could probably get away with doing that. Just putting in a 2 because it's in a different slot. Well, look at that. So we would have to go through and edit these tags to give them new aliases. And in this case, really all we got to do is change that 2 to a 1. You can't double click on it and do it here. Okay, you have to edit the tag and then go here, backspace 1. Notice instantly, if you're working on a tag and all of a sudden the rest of it turns reverse video, it recognizes it. Do one more here. Edit. See, no reverse video yet. As soon as I type in 1, it goes, hey, I know who that is. Apply. Okay. Notice the E's are gone now. So this is a happy rung again, folks. Okay. So there we've added digital I/O to your data neighborhood. And there are a couple more cards out there. And there is another feature called Discover Modules that maybe we'll show that in a later lab. I'm not set up to do that right now, and that was not part of this lab. So in this lab, we had you add in all of the I/O modules. So next were the analog modules. So we'll go do that now. So we'll finish up this section. So right click, new module. And you could uncheck this, check analog, uncheck this, check Allen Bradley, and then that's just the Allen Bradley analog modules. Or, because I'm lazy, I would just type in OF, and it's a 2, so it's easy just to go OF2. Now, there's 3 of them that have OF2. See, OF2, OF2, OF2. We just have a 1769 OF2. So double click, and I call that, this is the analog output. I called it analog out 03. And it is 2.1. So we'll just disable the keying anyway. Since slot 3, hey, we're good. Now you could go to connection and say, okay, I want to inhibit this module. If you do that, then the processor does not consider it as part of its territory. Or you could uncheck this so it doesn't fault the controller if the connection fails when in the run mode. But in this case, we want to leave it that way. We'll leave the RPI 80. So that means that this output analog card wants to have its internal data updated every 80 milliseconds. And you can set that anywhere between a half of a millisecond, which would be, I guess, 500 micro, and 750 milli. So that's a fraction of a thousandth of a second to 750 milliseconds, which is 3/4 of a second. Configuration. Now we'll enable both of these outputs. You can change the range. So you've got all of the popular ones here. Probably the most popular one is 4 to 20 milliamps. And you're thinking, well, that's strange, because right down below it's 0 to 20. Seems like 0 to 20 would be easier to scale and range than 4 to 20. Well, that may or may not be true, but with 4 to 20 milliamps, what do you have that you do not have at 0 to 20 milliamps? What you don't have is this, 0 milliamps. 0 milliamps is irrelevant if you're set 4 to 20 milliamps. Meaning, if you have an open wire, you've got 0 milliamps. If you're using this one, well, at 0 milliamps, you don't know if there's nothing or really nothing, meaning 0 from the device or 0 to the device, or if the wire's broken. If you use 4 to 20, then you're going to have at least 4 milliamps all the time. And so 4 to 20 is probably the most popular because it gives you that robustness. But we're going to leave it, plus and minus 10. And you can also pick different data formats. We'll just leave it in the default because that's really not part of the slab. So, okay. Now we have, see, we have that one defined down there now. Whoa, holy moly, look at there. We got 3 new tags, folks. Configuration, input, and output. Now, let's change this to IF4. It's easy just to type in IF4, not IF, and then dig it out. So let's take the 4 out. See, we got a few more choices in there. We have an IF16 and an IF8. So if we add the 4, that eliminates those. This is not the combo card. This is what we had before on the L35E. Okay, this is just 4 channels. So this is 2 separate analog cards instead of a combo card like we had before. We will call this analog in 04. Let me look at the notes here just to make sure that I'm doing it exactly the way you did it in the lab book. Yep. Analog input 4. Okay, it's already 2.1. We don't need to change that, but we will go and disable the keying just for grins. It's in slot 4. We're all set. Okay, so we can close that. Now we've got 4 modules down here, and we have a few more tags. We've got IF4s, and now remember these are in alphabetical order. So we still have this tag and this tag from the IQ16F, and it now also supports the IQ16. And then we have these 3 tags for the digital output card. We have these 2 for the analog in, and these 3 for the analog out. Now there is more code in here that we didn't straighten out. If we go back up to task, line 1 conveyor, I think that we have, well, the only tag is this one right here, and we'll edit that, and basically we put a 1 in there. Now this routine is happy. If we go to main routine, of course nothing there. Now for here, we'd have to do the same thing all over again, okay? Because all of these are slightly out of whack. I'll hit the geyser button up here. See the plus minus? Plus makes it bigger, minus makes it smaller. I call this the geyser button because if you're 40 years of age or older, which I am, then you're a geezer. That's an Old West term. Actually, they use it in Great Britain as well. But out west, they called cowboys that still rode the range at 40 years old because that was old for a cowboy. Usually you got killed before you hit 40. If you were 40 or over, you were a geezer. Now that was not a slam. or necessarily detrimental. But the young cowboys would tell the girls he's a geezer, meaning he's too old for you. I kind of extrapolated onto that. At 40, you're a geezer. 60, you're an old geezer. At 80, you're a super geezer. And 100, you're an ultra geezer. And of course, women are never squeezers. So if you're 40 or over and you're a female, you're not a geezer, you're a squeezer. So you got squeezers, old squeezers, super squeezers, and ultra squeezers. And just so you ladies don't get offended, think about your aunt. When you were a kid that would come to visit, she'd squeeze your cheeks. She'd come up and kind of pinch your squeaks and then give you a big hard squeeze. That's why I call them squeezers. Older women tend to squeeze kids a little harder than younger ones. Yeah, that was a terrible trail I got off on you there. Sorry about that. We're not going to go through and change all these because that's really not part of this lab. So the next part of the lab, we're going to add communication modules. But I'm going to stop here and then create a new one because this one has gone well beyond my 20-25 minute target. So I'm going to stop right here and pick this up in another section. Thank you. Thank you for watching this lab discussion from Volume 1 of An Introduction to RS 5000.